this was some work that I did. So you see, it puts Guruswami's affiliation as University of Washington, which it no longer is. He's at Carnegie Mellon. He was there when I did this work with him and with Amit Chakrabarti, who was visiting from Dartmouth there. And then I went home and continued working on this and eventually roped my father into this. So that's why he's a sort of another author on here. Okay. Now, I guess I'm going to, actually, I should probably start with the motivation a little bit before the definition. And just a little bit of motivation is that there was a bit of a flurry of interest in evaluating search engines or retrieval systems and that kind of thing in the information retrieval community, maybe 05 to 07 or 08 or something like that. I think it's still of interest, but not quite the level of papers that you saw at that stage. And so one thing that happened was that some people said, well, maybe the metrics people are using to evaluate these things aren't right, we should try something different, which also inspired me to think, well, maybe what can one prove theoretically about these sort of results? Okay. So the question that we're interested in is this: we're given a vector A of weights between 0 and 1, okay, because they're bounded, and we've got non-increasing weights, okay. And these are known to us in advance. That's very important. But what's not known are some other quantities y between 0 and 1, which somehow represent something like the relevance of something to a search query. Okay. And so yi represents whether or not the ith item returned by this retrieval system is in fact relevant to our query. And what we want to compute is the score. So I'm interested in linear scores, which is to say sort of a weighted average of these things. Now, why weighted? Because you care much more about whether the first few things returned by the system are relevant than whether the 100th or 300th item is relevant. And this makes the problem. This makes the problem of estimation inherently actually easier, or at least depending on the weight family, easier than if it were just sort of a mean. Right? If we just took, well, let's work out how many of the documents returned are relevant. That's somehow actually a harder problem, as I'll show you, than working out the weighted mean. Okay. So what we want to do is come up with a good estimate for this weighted mean, and we want to look at as few y values as possible, because those represent asking somebody to actually read a document and assess whether or not it's relevant, and it's expensive, so hence this sort of query complexity model. And what we're going to do is produce a good estimate with a few.
N and A are given.
N and A are given, indeed. Although we're going to be doing some sort of asymptotic things to do with. We sort of, N, whilst it's given, we're going to imagine can be as large as we want in some sense.
But it's not the increasing after each query.
No. Okay.
Are you going to be giving a more precise definition of the model later? Or
not necessarily.
So in that case, can I ask a question?
Yes.
So do you get to choose which of the y's you want to look at?
Yes.
Or is it coming from some?
No. So you're told the A's, you're told the N, you're told that there's hidden Y's, and you can choose whichever one you want to look at.
Okay.
And at unit cost to look at each Y.
Okay. And your notions of approximation and other things.
I'll explain that in a moment. Yep, sure. So that I will define a bit more carefully. Okay. So I've already spoken a little bit about that, why we're doing this, but I thought that query complexity was a sort of a nice thing to do, and I have a paper some years ago on communication complexity, which isn't terribly far away, so I thought, why not revisit something that worked in the past? And one thing I should point out is that this issue of metric, I've got implying a sort of linear metric here, but that's not necessarily what the community uses. They often use things like mean average precision, which is sort of an inherently quadratic kind of quantity where you're multiplying some of the yi's by other yi's. I mean, they've got other justifications for it, but it ultimately turns out to be a quadratic metric. So much of the research you see is in trying to get good sampling strategies for these slightly more complicated metrics. But I thought, well, we don't really understand the linear ones first. Let's try and get some better appreciation of that. Okay, so you could imagine a kind of a decision tree, which is a sort of randomized decision tree. So you can make choices at all of the nodes in the trees as to which item you're going to look at. So you can sort of have some coins or dice or whatever you've got from random number generator, and you say, okay, I want to look at this document, or I want to look at that one, and so forth. And at the leaves of the tree, you say, okay, I believe that the weighted mean is this. So we've got this randomized decision tree, and we accept that it might fail with a probability delta, and we also accept that it might not get exactly the right answer. So we're going to say that the sort of relative, we're going to classify this as a relative, not relative, absolute error between the estimate we obtain and the actual value. Okay, so we're going to say it's an epsilon. The epsilon delta approximates if with probably 1 minus delta, we reach a leaf that whose absolute difference from the thing we're really trying to estimate is at most epsilon. So one of the bugs in my slides is on the next line where it said these people show that this many samples suffice to estimate the mean. I think it should read that you need at least that many to estimate the mean. I don't know why I wrote suffice, but anyway. So there's a lower bound, which is 1 on epsilon squared log 1 on delta, which is something that people have seen before in different contexts. Okay?
Is there some bound on the y's?
Sorry?
Is there some bound on the values of the y?
Oh, yeah, so the y's, everything is constrained to be between 0 and 1.
Okay.
So you could imagine that in some sense they are 0, 1, strictly 0 or 1, but you could also say that there's a concept of, it won't hurt you to allow partial relevance, in a sense.
So I missed something. What's the probability underlying this random process?
So it's up to you. So you can choose to sample this or sample that. So you can imagine this sort of decision tree with probabilities at the nodes of the trees.
The AIs are drawn from some distribution.
No, the AIs are fixed. So I'll just go back. I mean, one thing okay, so I'll just retreat a little. So the AIs are given to you, N is given to you. The YIs are given, but they're hidden. And it's up to you to choose which YIs you want to look at. And in a sense, the probability is entirely to do with your choice of samples, in some sense, or the choice of the Ys that you look at.
Okay. So you're choosing them randomly?
That's right.
I see. Okay.
And so that you have a relatively high, like 1 minus delta chance of succeeding.
I see.
You hope the delta is very small. You also hope that epsilon, which is the error you obtain, is very small.
Okay, thanks.
Sure. And it's important to get this right, and I admit sometimes that each time I present this, I get slightly different questions about the model, and it's sometimes good to just stop and make sure people are working out. Okay, great. So it's known what the sort of hardness of the mean question is. Okay, but as I said, it might be that because some of these documents are sort of more important than others, that somehow we can afford not to look at quite so many things as if we were just calculating a mean. Now, so as well as this 1995 result, Zidbar Yosef, who's also a Google person, though not here, described two things in a paper in 2001, and one is block sensitivity, which is it says, okay, there's certain parts of the input that we haven't looked at, and I'll explain more about that later. And also, they talked about another technique for getting a lower bound on the mean, which relates to some work by some statisticians originally. Okay, so let me show you what we sort of did. So, okay, so the weighted mean problem in general is a sort of a more general problem than the mean, and so if you didn't care anything specific about the weights, then we showed that okay, in the same number of queries you can match the lower bound to the mean. But that's not particularly interesting because maybe there's something interesting, maybe there's something special about the families of weights that are interesting. So so we look at 3 different weight families. One is geometric, which is inspired by some work of my colleagues who believe that you ought to have geometrically decreasing weights to evaluate retrieval systems. Another case we looked at was where the weights sort of diverge. So you could imagine that N is sort of really, really large, and then these A's form a divergent series. And that turns out to be as bad as the mean case. Okay. I mean, the mean is clearly a divergent series because the weights are just 1, 1, 1, 1, 1, 1, 1, 1, 1, whatever you've got, some constant repeated.
So the weights are Y's?
The weights are the A's.
Oh.
So the problem changes depending on what it is that you're trying to estimate.
No, I understand.
So if you've got these weights that go down very quickly, it's sort of easy because you can look at the things with heavy weights only. On the other hand, if the weights form a divergent series, then it's as bad as the mean. And so, I mean, it would be nice to have a general sort of theory here, but the best we could do is something in between case with the power law, which is the most interesting one, which sort of converges, but doesn't converge as quickly as the geometric case. Okay. Here is a particular flavour of the Höfting or Chernoff bounds that is most useful to us, and a little aside that I've been giving when I presented this is that, I did an undergrad in statistics and yet never learned about Chernoff bounds. I don't know whether Lawrence ever. Did you ever hear about Chernoff bounds?
Yeah.
You did? Okay, so I came to my PhD, it's like, what's this? Chebyshev's inequality, Markov's, what's this? Chernoff bounds, and I guess, computer science theory people are interested in slightly different questions sometimes from the statisticians. Okay, so I actually went back and tried to find the form I wanted. I actually went to JSTOR and retrieved an old paper from 1950 something by Hefting. Okay, so the form I want is this, where you've got these bounded independent variables, okay, so they're between 0 and 1. I don't know that they actually have to be, I assume I've written this correctly, I don't believe they actually have to be identically distributed, they just have to be bounded and independent. Okay, so you add them together, and you look at the sample mean, and the divergence of that is nicely bounded, inverse exponentially. Okay, so what do? The A's are essentially going to be a unnormalized probability distribution for us. We normalize them, we do sampling with replacement with unequal probabilities, which we can do quite easily. Okay, we choose, at each trial, we choose a particular item with a probability specified by its normalized weight in some sense. Okay. And then if you do some algebra, you can find that with 1 on epsilon squared log 1 on delta approximately trials, you can get the right accuracy. Okay. So that was nice, but not very informative so far. But we think, well, what can you do with these A's, right? So that was, yes?
Just a comment, it's kind of a lot of computation because if n is large, you're computing all these. Like I was thinking there'd be something more adaptive, I guess. In that particular algorithm, we're computing n different probabilities and then choosing the y's with those probabilities.
Oh, I see.
I was thinking something more adaptive. I don't know, like find the largest. You have a power law assumption yet, or not yet?
No, that's just purely generic. So you can have this works for any family of A's. It's just showing that even though weighted mean in general is a sort of seems like a more general problem than mean, it really is sort of the same complexity in some sense.
I see. I think I'm just jumping ahead then.
That's a reasonable thing to do. Okay, so maybe some of these A's are more important, because of the weights of the A's, some of these things are more important than others. Okay, so what we're going to do is say that some of the items are what we call heavy, and we're going to definitely sample those. Okay, so that maybe we're sure that somehow we ought to look at the top 10 documents or something like that, and then afterwards we'll run this generic scheme that I described, except that we'll re-weight everything. So we'll re-normalize the weights, okay, based on what's left. Okay, and this scheme appears in 2 other instances. So I discovered only fairly recently that some people at Stanford in 2006 worked on a somewhat similar problem, and I have to admit something strange about this paper. So another aside about this is that it hasn't actually been appeared anywhere yet. We submitted it somewhere and it got rejected, and you see what the guys at AT&T said was it wasn't fair that Moses Charakar was my advisor because I never got the experience of having a paper rejected. And this is an important thing to learn when you're a PhD student. So this was my first paper rejection. I got to be shocked. I thought, what do I do? So I somehow haven't got over that yet, and we still haven't resubmitted it. But that's also because I need to just read that thing by those guys at Stanford carefully to know exactly what to cite from them. Okay, so they have a sort of similar scheme with these. Some things that are heavier and some things that are lighter and so forth. Okay, this also appears actually in the statistics literature. So it took me a while to work out what the relevant statistics literature was, and it turns out that it's you have to look up survey sampling is the sort of keyword that you want, and they have situations where they want to minimize variance, say of some unbiased estimator for something, and they again have situations where that is what you call a list sequential strategy, which is what we're sort of doing here, where you sort of we're actually doing something that's sort of kind of draw sequential, but anyway. They have a situation where you sort of walk along each item and say, okay, do I look at this, yes or no, with the different probabilities. And they have some things where you've got probability 1 at the beginning, and then other things that sort of it drifts down to something lower. So this has appeared in other circumstances. Okay, so we've got the heavy ones, we do the generic scheme of the light ones with the rescaled weights. So what do we get? We get h, or little h, which is the number of heavy things, plus this 1 on epsilon squared log 1 on delta appropriately scaled. Okay, and it seems like a good strategy, but what's the appropriate H to use? So one thing is to say, well, maybe H ought to be all of the terms that have a normalized weight of at least epsilon over 2, or something of the order of epsilon anyway, right? Because if there's something with a weight that's certainly larger than epsilon and you don't sample it, then you're guaranteed to be out. I mean, not guaranteed. There's no way you can guarantee that you're within epsilon of the right answer, right? So, okay, you think, well, let's look at those things, and then
because it's an additive epsilon. There.
Because it's an additive error, right? It's not a relative error. So some people have worked on. So some other papers have worked on relative errors actually. Okay. So we want an additive error. So you have to look at some of these terms, and then somehow, we'll just do the generic scheme on everything else. The problem is that if you look back at this formula here, we might end up with a situation where the second term is actually significantly larger than the first. And one of these sort of rules of thumb that you learn from doing this research is if you're adding two things, you're trying to minimize their sum, it's probably a good idea if the two things are roughly equal. Mm-hmm. So somehow you don't want the second one to dominate the first. So in fact, what we're going to do is to make H larger, and then somehow have the contributions about the same. So we try this with the power law case, for instance. Okay, so we've got a convergent series, and we set everything up, and then we have H items, and the weight of the light things is going to be roughly, if you do the integration, roughly sort of H to the 1 minus P over P, right? You just think about the integral, approximately that. Okay, assuming that everything works nicely with N and H and P and so forth. And if you do a little bit more algebra, you find, okay, so H should be roughly epsilon to the power of 2 over 1 minus 2P. Now, don't ask me why that sort of makes sense, but it just sort of pops out in some sense. And I thought, all right, well, that's an interesting quantity, but it certainly balances, and maybe it's indeed the right answer. Okay, so we then claim, okay, that if you do this, roughly this many multiplied by log 1 delta, then if you query that many things, then you'll get a good bound. Now, note that this is lower, or this is better, than epsilon to the minus 2. Right, so when P equals 1, for instance, what do you get? You get 2 over 1 minus 2, which is whatever, epsilon to the minus 2. Right? But as P increases, then this quantity is going to be smaller. All right, so that seemed like a useful thing to do. But the question is it in fact the right answer? Could we get a matching lower bound? And that actually took quite a while to work out. So, okay, so we can refer to the paper I mentioned before. So, if assuming that epsilon and delta behave nicely and the n on 4 part doesn't dominate, you've got this sort of fairly precise formula for a lower bound if you want to estimate the mean. Okay, so we're going to use this result fairly heavily because we're going to somehow fake the mean problem using the weighted mean problem. Even though, now somebody yesterday said to me, well, wait a minute, isn't the weighted mean problem more general? And so therefore it doesn't include the mean. But we're going to do a reduction from mean to specific kinds of weighted mean, which is a weighted mean with a certain kind of certain A vector. Okay, so let's talk about block sensitivity for a moment, which seems to be a fairly powerful tool. Imagine that you had some part of the input, these hidden y's, say, and you said some adversary changes all of their values, maybe from whatever they are to something else. What does this do? What could this potentially do to the output? So if it changes the output by at least 2 epsilon, then you know that you have to look at something in that block. Otherwise, there's no way you can guarantee that you're with an additive error of epsilon of the truth. Okay, so then you say, okay, maybe there are several blocks like this. Like there's some part of this, here's one part of the input, and you must look at this, and here's another part of the input where if you change the values, the output might change by at least 2 epsilon, and another part, and so forth. And so you know, if you've got these disjoint subsets of the input, you know that you have to look at least at something in each of these. Okay. So this, you've got, so here you've got to multiply by 1 minus 2 delta, but basically, and there's a slight difference because you've got expected query complexity, but in any case, it's still a reasonably powerful technique. You can multiply the block sensitivity by 1 minus 2 delta, and that's a lower bound. Now, if you think about the weighted mean problem, at the very least, you've got to look at every item whose weight has normalized weight is at least 2 epsilon, right? Because if it changed from 1 to 0 or 0 to 1, potentially then the output moved by at least 2 epsilon.
So it's a block by itself.
So yeah, so that's a block by itself. But that's a rather extreme case.
So block is for which the worst case change would cause at least 2 epsilon.
That's
change.
right.
Okay.
Okay. So so that was one sort of tool we're going to use. The other thing I mentioned was that we're going to use some reductions. Okay. So again, the slight flaw in this slide is that the term weighted mean up the top there should probably have an accompanying A vector, right? Because weighted mean in general is of course a more general problem than mean. But what we're going to do is to reduce the mean problem. We're going to fake the mean problem with the weighted mean problem with a specific A vector. So we're going to say, okay, if we're going to set up this instance of the weighted mean that sort of almost solves or approximately solves the mean problem. And then because the mean problem is hard, that must mean this weighted mean problem is also hard. Okay, so what we're going to do is something fairly obvious. We're going to sort of partition the weights in the weighted mean problem into some subsets that are roughly equal. Okay, so that the weights, if the weights in the weighted mean problem, if you sort of glue them together somehow and the glued sets become almost the same, then somehow you can fake the mean problem. Okay, we're going to say, well, if this subset of what we're going to associate this subset of weights with a particular and their accompanying y values with a particular x value up here, we're going to say whatever this x value was, the appropriate y values down here are going to be the same, and then maybe some of these weights don't actually appear in any subset, but that's okay, we just throw them away and assume that the y is 0. Okay, now note that we don't actually make any, we don't somehow really copy the x values into the y's, and of course we're just sort of making references so that whenever you query this y, you query the appropriate x. Moreover, every time you look at a new x term, it forces you to look at a new subset and therefore a new y term, right? So any lower bound on the x's is also going to apply to the y's. And the other point is that we're not using any fact about the x's to determine these subsets. It's purely something to do with the weights and their nature that determine these subsets, and therefore how hard the accompanying weighted mean problem is. Okay. So we're going to choose the subsets so that somehow the consequence and the weighted mean that we end up with is very close, so within epsilon of the true mean of the mean problem, and therefore if anything that were an epsilon approximator of the weighted mean is also going to be a 2 epsilon approximator of mean. That's how we're going to kind of obtain our lower bound. Now, let's start with, so we're going to start with 2 sort of warm-up things, and then we're going to get to the more interesting one, which is the power law weights. Yes?
Is it easy to choose such subsets? That kind of flashed by very quickly.
I mean, it depends. We'll see. So in some cases, yes. In power law, it took me a few months on and off thinking about how to do this. I mean, it turned out to be kind of nice in the end, but I couldn't quite get my head around what one needed to do. So that's the interesting part. I'm leaving that as the dessert for the talk.
Okay.
Okay. So let's look at some easy stuff. So geometric weights. I mean, it seems to be kind of obvious what you do here because somehow you've got these very heavy weights at the beginning, and then this tail that sort of doesn't matter, and somehow the size of the tail is proportional to, the weight itself, or the weight the next weight, say, or something like that, right? So seemingly, the obvious strategy here is you sample some things down to some point, and then you just throw the rest away. But you might as well make it rigorous. So my colleagues believe, have sort of published something that sort of says, well, we really should be using these geometrically decreasing weights because this models how humans read things. They say, oh, do I follow this link? Oh, maybe follow the next one, and then this. So a human is sort of reading the outputs of a retrieval system as sort of a geometrically decreasing interest in some sense. Maybe that's reasonable. Anyway, if you want to obtain a simple lower bound, of course you must look at every BI that's at least 2 epsilon, and you do some slightly annoying things, and you end up with something that's approximately log 2 epsilon over log q, and log q is of course negative, so you essentially got log of 1 over epsilon. Okay, now remember that epsilon is small, so 1 over epsilon is large, and so log of 1 over epsilon is a lot better than 1 over epsilon squared, which is our generic lower bound. Okay, and in particular, it's also an obvious upper bound because you can just at some point throw away the tail, right? So if you look at the tail terms, and if their total weight is at most epsilon over 2, you say, well, they can't affect the answer very much. You don't even have to look there. And somehow the position of where that tail starts to where the sort of lower bound in some sense position ends is sort of within a constant determined by q, right? So there's obviously these upper and lower bounds match each other within a constant. So instead of epsilon 1 and epsilon squared, we've got log of 1 and epsilon being the appropriate number of samples we need to take. And in particular, in the geometric case, you just look at the stuff at the beginning. Not very exciting, but it's worth sort of laying some groundwork. Okay, so something a little bit more interesting is what happens when the weights diverge. Okay, now it turns out in this case that the problem is as hard as the mean problem. Okay, so what do you do? Well, you're going to sort of fake the mean problem by collecting together blocks of weights that are sort of roughly the same. And in the divergent series case, and we're sort of assuming that n is really, really big here, okay, we can do this because we know we'll never run out of weight because the weights series diverges. And we also know that the weights themselves are bounded between 0 to 1. So somehow by taking lots and lots of weight, we can get these clumps that are kind of roughly equal. So what we do is we keep taking weights until we get a sum that's at least somewhere between 2 over epsilon and 2 over epsilon plus 1. And we know that we can do this because of the bound and the fact the series diverges. So we carve that off, and then we take another chunk of weight between 2 over epsilon, 2 over epsilon plus 1, and so forth. And if you sort of add things together and so forth and use the 1 over 24, whatever the thing is, and you get exactly that many subsets, then you can somehow estimate the mean within epsilon over 2. So I guess this time we're doing an epsilon over 2 plus an epsilon over 2 approximated for the mean, and so forth. So you can. It's not too hard to fake the mean problem here because you can just take consecutive chunks. So in fact here the obtaining of the subsets is quite easy. Okay. Now the one that the thing that was kind of a bit more interesting is what do you do in the power law case? So we thought, okay, well, let's start with using block sensitivity, which is my first thought. And so you group together contiguous sequences. So you start with that some of the weights are just really big, at least 2 epsilon. So you treat those as a block by themselves. Then afterwards you form contiguous blocks of weights that add up to at least 2 epsilon.
Can I go back one slide?
Sure.
If I understand your results, you said for every fixed delta, so you fixed delta and then reduced mean to weighted mean, right? So you didn't obtain a sort of a lower bound in terms of delta, or
so the delta is not the particularly interesting part in a way. The epsilon is the sort of.
I can believe that. I was just confirming that.
So you sort of fix the delta, and then it's the epsilons you play with, right? So that there's if you can estimate this within epsilon over 2. If the gap between the mean and the weighted mean is epsilon over 2, and you've estimated the weighted mean within epsilon over 2, then you've estimated the original one within epsilon, and so you know that's hard, so therefore you know this other thing must be hard.
And delta is hard, yeah. Okay.
Sure. Okay. So, all right. So in this case, we've got, so recall we've got these very heavy weights. We have to look at each of those items individually, and then we look at blocks of contiguous weights that add up to at least 2 epsilon. Now, note that those blocks are going to be a weight between 2 epsilon and 4 epsilon because by that stage, we know that all the weights larger than 2 epsilon have been dealt with. Right? So we don't overshoot by too much in some sense. Okay. So this gives us a bound on the block sensitivity of the number of very heavy terms plus the remaining weight of stuff divided by 4 epsilon. Okay. That seems to be the number of blocks you obtain. But unfortunately, if you do this, you end up with a lower bound that I've left out the delta part and the expected and so forth. But the important point is you end up with a bound that's something like epsilon to the minus 1 over p, which isn't as quite what we hoped. Right? We wanted to get epsilon to the 2, assuming that what we did with the upper bound is correct, and I believed it is, I know now that it is, that I wanted to get epsilon to the 2 over 1 minus 2p, and we didn't quite get that. Okay, so what then? And I spent some time thinking, well, maybe I can use some property of these power law terms, and I'll actually look at, I must have been naive or something and thought maybe I can use something about the properties of these sequences to add certain terms together, and they'll end up being about the same. And I thought, well, this is no good. And of course, one doesn't actually need to construct this thing. One just needs to describe a method for constructing equal weight subsets, even if one doesn't do it explicitly. right? And it took me a while to sort of appreciate that point. And then I started thinking, well, what is this? What is this? Oh, sorry, I haven't actually explained this slide yet. But what does this look like? I'll say that in a moment. So just a little bit more precisely, what we're going to say is, imagine what we want to connect are these subsets of weights that are somehow between rho and rho minus epsilon over 2m. So we've got these m subsets. We want them to be almost equal. Okay, and then it means that oh, I see. I can sort of do this. Okay. So it then means that this weighted mean that we obtain is somehow something between rho multiplied by the total sum of the x's, or within epsilon over 2 over that. Okay, and then if we do the appropriate division, we're getting with the probability 1 minus delta, we're getting an epsilon over m times rho approximator for the mean. Okay, it's probably too many formulas on this slide actually. I've been somewhat put off doing slides of this style. It's a bit old. Okay. So what's the interesting thing? The interesting thing is, how do you actually obtain these weights and collect these weights together to be roughly equal? And I remember thinking to myself, well, maybe it's something like bin packing. And I think I had a conference deadline I was aiming for this, and I still couldn't work out what to do. I thought, maybe if I tell myself I'll make the deadline, then I can do it. And it sort of worked like this, and I thought, well, maybe it's bin packing. And then I went to my father and I said, what if it's this? And it was so the reason he got brought into this was through a discussion with him. He said, no, I don't think that's actually what you want to be doing. What you really want to be doing is a scheduling kind of problem. Oh, okay. And we talked about what might be good, and it turns out if you look at the last line of this, that the thing that we want to do is to the thing that inspired us was the problem of maximizing the minimum completion time. So you've got some problem with jobs, and you've got m machines, and you assign these jobs to these machines, and you want the machines to sort of all finish at around the same time. So you want to maximize the one who finishes first, in some sense. You want to make that as late as possible, and then somehow that will mean that everybody finished kind of near to everybody else. And it's a rather strange objective, and there aren't a huge number of papers on it. I talked to somebody, Gerhard Verginger, about this, and he's one of the people who worked on this, and he said it had something to do with aeroplane construction, but we never finished our discussion for some reason. I'll get to the bottom of that one day, why anyone cared, but I cared for a different reason, which is I was trying to make these equal subsets. And it turns out that this longest processing time strategy is a good thing. So you start with the job that takes you sort the jobs in non-increasing order of duration, and as you sort of proceed in time, you assign a job to the first machine that's available. So you sort of sort them and then assign these jobs. Okay. And this is a bit like what we've got, because we've got these A's and they're in this decreasing order, and then somehow we want to assign them to these subsets so that they end up being almost the same at the end. Yes.
In the scheduling problem, don't you want to minimize the maximum, not maximize the minimum?
Well, it depends. No, normally one does want to do that, yes. But this is an unusual scheduling problem in which we want to maximize the minimum.
Which you reduce to this problem.
No, I understand the reduction.
If you put too much weight in one of the buckets, that's okay. That's right.
Well, no, I'm just saying that there are many scheduling problems around, and this is a somewhat quirky one that only a handful of people looked at.
Okay.
And it so happens that it relates to what I want to do. But, it was just fortunate that someone had thought of this.
So is there some reason why minimizing the maximum would not be good for you?
Well, it doesn't necessarily make things equal. Right. So, well, I see what you mean.
It should.
So you could have the maximum and then... Well, I guess it's sort of the same thing, isn't it? I don't know. I mean, I don't know why I ended up looking at this rather than that. You'd have to ask me that 2 years ago. Or something why I thought of it. A good point. I don't know. I guess I had this fear that maybe you could still do that and somehow end up with something very uneven. Perhaps not. Anyway. So there are various strategies that these papers use, but one simple one is to use this longest processing time heuristic, and I thought, well, maybe this helps us. So what do we do here? So we have these jobs, and what we're concerned about is the tail. Okay. So imagine we have a job that has a very large tail after it, so large that if we add up all of the the jobs of the few things, the A weights afterwards in the tail, and divide by m minus 1, so like the number of machines minus 1, if that's larger than the duration of the current job, then somehow we know that the difference in the machine completion times is at most the duration of the next job. Why do I say that? Okay, so you'll see why that's true in a moment.
Otherwise, the greedy algorithm would have scheduled it there, in that gap.
Well, there's sort of not enough time to finish everything, basically. So, okay, so here's what happens. So consider the last job that finishes. Okay, when that job started, all the machines were busy, or perhaps that was the very first job. Okay. Now imagine that this tail is, you've got this large tail of jobs that you still have to do, okay, and that large tail divided by minus 1 is still greater than the duration of the current job. Okay, so we're saying this last job to finish. So here's this job L, this last job to finish, and we've got this large tail of stuff. We're going to assign it to all the other machines while this one is working, but somehow this tail is so large that there's not enough machine capacity in the time in which it's supposed to finish to do everything. Because there are n minus 1 jobs, and that we've only got time TL, if you like, times those n minus 1 machines, to finish everything else. So if indeed that tail divided by n minus 1 were larger than TL, then that would mean there would not be enough machine capacity to finish everything. In other words, this L could not in fact be the last job. Okay, so this can only be true, or something can only be the last job when the tail is sufficiently small. Okay, so this capital N was kind of like an indication of which jobs were sort of had very large tails. Okay, so this is my final slide, almost final slide in some sense. So what this made me think is, okay, this is good. So I know that I can now place a bound using this LPT. I can now place a bound on the finishing times of everything and guarantee that somehow, while the tail is too big, that knowing some properties about the tail and so forth, I can now say that I can guarantee what the difference in finishing times between these machines are. In other words, what the error between the subsets is. Okay, so we wanted to get epsilon to the 2 over 1 minus 2p, okay, and we know that at some stage, at least, up to some capital N, the tail is too large. So we sort of, we set, anyway, well, it's a somewhat confusing slide, but we set the R, the M, and the rho almost to do what we want. We can't quite get it right. So we can estimate the size of the tail because it's just a sort of an integral, because it's a power law. Okay, and when we sort of set everything up, we find that we almost get what we want. We do, in fact, get a lower bound of epsilon to 2 over 1 minus 2p, but we also, unfortunately, get a divided by p squared in there, which, depending on how you look at it, may or may not be important. So you can, in fact, fake the mean problem with the weighted mean problem by applying this LPT heuristic, getting all of the subsets about right, and then there's these are somewhat crude estimates, right, based on these integrals, but so that's sort of, it's the crudeness of the estimate that's probably causing the p squared to be in there in some sense. Okay, so I guess the main thing I'm interested in is what to do next. So one thing is I'm actually looking at some more pragmatic. So this was a kind of fairly abstract thing that I don't think the retrieval people would care much about. But I'm actually trying to sort of look at some estimation techniques that minimize the variance, say, of these estimates. So with some unbiased estimators, and what the right thing to do in that case is. The other two things are, well, okay, we've got divergent weights, we've got very convergent weights, and we've got these power laws that are something between, but maybe this doesn't actually, it'd be good to capture something a bit more generic. Like why is it that this mode changes from log of 1 over epsilon, then to this epsilon to the 2 over 1 minus 2p, and then to epsilon to the minus 2, and what's, how sensitive, like if you had slight changes in the weights, because some of these series look somewhat similar, like what's happening and why. And to do something more generic. And of course, the third point is that the most interesting question is to actually compare multiple systems at once, right? Because we're only concerned about doing sampling to estimate the performance of one system. So of course, you've got lots of common documents, and they appear with different weights according to different. One system may give a document a very high weight, another one a very low weight, and so forth. And maybe what we want to do is minimize the sum of the variances of all these things, or it's not clear what you want to do. One thought I had, the right thing to aim for, is that what you're ultimately producing is a ranking of these systems. So you want to sort of say, maybe with high probability we got the ranking correct, and that's ultimately what you're concerned about. So how many things do we need to sample so that with 95% probability we actually got the rankings of these systems right. So just wanted to thank those people for hosting me, although no one's actually there, none of the authors are actually there anymore, and my colleagues Alistair Moffat and Justin Zobel, and then William Webber is a PhD student of Alistair Moffat's. And just one last little story is that William and I used to sort of see each other around the department for about a year and not talk to each other and just grunt at each other as males often do. And in fact, the thing that got us started talking and then led to some of this was that I discovered he went to the same school as me, and Lawrence for that matter too. And suddenly that made us start talking. It's a very Melbourne story, I think. Okay. What happens now?